Kia ora koutou. This is the last question I'm going to do tonight, and this is sort of for Miguel. This is the whole question from last year's paper that the A-level class sat, and it's the vectors one. So please make sure you watch the third part, where we have to use the formula for the distance from a point to a plane. There are 3 parts to this, and that's really the only bit that you have to think about a little bit. And then after you've watched this video, if you are watching the night before exam, please get to sleep. Right, so we start off being given 2 planes and a line, right? So we've got planes M and N. The equation for M is this one, and the equation for N is this one. And here's the equation for the line. So the first thing we have to do is show that that line L is parallel to M. Then we have to find the acute angle between 2 planes. So for that one, we should be thinking about the normal vectors to the planes, and then cos theta equals this, the dot product divided by the 2 magnitudes. And lastly, we've got this one. We've got a point lying on a line, and we're told that that point is 2 units away from the plane N. You've got to be quite careful in this question to use the right things here. I remember when I first did this question during last year's exam, I spent a couple of minutes getting all muddled up about what was M and N. That wasn't good. And then find the position vectors of the 2 possible positions of P. Right, so I'm going to go quite slowly through this. Just put it on 150 speed if you need to. So let's start off by just writing out the equation for the plane M is 3x plus y minus 2z equals 10. And then the line L has got vector equation written in kind of combined form, 4 plus lambda, 2 plus lambda, 1 plus 2 lambda. And we have to show that this line is perpendicular to the plane. So as usual, we'll start with a bad picture. Here's the plane, and here's the normal vector. Let's do that with a different colour. So the normal vectors, well, this is a normal vector to the plane, right? There are many, many of them, infinite numbers, and we have to show that the line is parallel to the plane. Right? So the line could be lying down here, but the key idea here is that the normal vector to the plane and dot producted with the direction vector of the line should equal 0. Okay, so what's the normal vector to the plane? Well, it's 1. Where are we? No, that's the direction vector of the line, 1, 1, 2. And the normal vector to the plane is 3, 1, negative 2. So we want to show that that equals 0. So please show you're working fully. Right, we need to show 3 plus 1 take away 4 is equal to 0. And then we have to explain. So the line and the normal vector are perpendicular to each other. So we can't say that the line is in the plane. We haven't checked that. But this means that we know that the line L is parallel to plane M. So that's the first part. Right, the second part of the question goes like this. Calculate the acute angle between planes M and N. Right, so we've got M is 3x plus y minus 2z equals 10. And plane N, x minus 2y plus 2z equals 5. So if we think about those 2 planes, here's one of them, and here's another plane here. We can picture that with 2 pieces of paper, and we can find either the acute or the obtuse angle. But the place to start is this, that cos of theta is equal to the dot product of the normal vectors, scaled by the magnitude of the normal vectors. So that gives me 3 squared plus 1 squared plus negative 2 squared for plane M times 1 squared. I'm just going to do this quickly, plus 4 plus 4. And the dot producting gives me 3, 1, negative 2, dot 1, negative 2, 2. So just make sure you're showing full working. So for the dot product we get 3 minus 2 minus 4 divided by the square root of 14 times the square root of 9, which gives me negative 3 over 3 root 14 Yes, you can chuck that in your calculator now, but nicer to write it like that. So that's cos of theta. Now, we should know we're getting a negative number there. So again, always thinking about this curve of the cosine graph, which next year's class are going to see on day 1 of school. If we're negative, that means that we're not going to have an acute angle, right? Because the acute part is in here. So just be on the lookout for that, and we get theta is equal to cos inverse of that. And in degrees, that gives me, to 1 dp, 105.5 degrees. So the acute angle between the planes is 180 minus that, which gives me 74.5 degrees. Okay, now the last thing we've got, let's go back and read the question, is this tricky bit here. So this is the bit that Miguel wanted a hand with, but he figured it out for himself, so that was good. We've got a point lying on the line, and we know the perpendicular distance of that point from the plane is equal to 2. So the formula that we want is the one that we went over in class today. We take our normal vector, and then suppose that my point has got coordinates alpha, beta, and gamma. I take each bit of the normal vector and I multiply them by that point. Right, and you know we've done the proof of this. And then we subtract off the constant in the plane equation. And we scale it by the magnitude of our normal vector. Negative 1 squared, n1 squared plus n2 squared plus n3 squared. So what we're going to do is we're going to solve that equation being equal to 2. And then we have to have a think about what we do from there. So, I'm just finding my bit of paper. Where's it gone? Right. So what's my normal equation? Well, the plane is x minus 2y plus 2z is equal to 5. And the general equation of the position vector on that line that we're looking for is 4 plus lambda, 2 plus lambda, and 1 plus 2 lambda. So this is going to give me the distance from any point on that line to that plane. So we're going to have 1 coefficient of that x, 1 times 4 plus lambda, minus 2 times 2 plus lambda, plus 2 times 1 plus 2 lambda, take away 5, scaled by the square root of 1 squared, plus negative 2 squared, plus 2 squared. And that whole thing has got to equal 2. So 2 is equal to, so working all that through, in here, I'm not going to do the expansion now because it's getting too late, but you need to do the expansion carefully because this is where you'll go wrong. Actually, I am going to do it now. So 4 plus lambda minus 4 minus 2 lambda plus 2, and so on. And we've got square root of 9 here. So I get 6 is equal to, well, the 4's go, negative 3 plus 3 lambda. So either, I get 2 solutions, and this is the thing you've got to think about. Either 6 is equal to the positive value of this, negative 3 plus 3 lambda, giving me 9 equals 3 lambda, lambda equals 3, or we get the other one, where we get negative 6 is equal to negative 3 plus 3 lambda. So negative 3 equals 3 lambda, lambda equals negative 1. So it's now really easy to see what's going on. We've got a line like this, and every point on this line is some distance from the plane. And when we've got lambda equals 3 and lambda equals negative 1, then we're exactly 2 units away from the plane. So we just need to chuck this value back in, and we get P1 or OP1 for the position vector is 4 plus lambda, so 4 plus 3, 2 plus 3, and 1 plus 2 lambda, giving me this vector. And then we do it again with lambda equals negative 1. And that gives me 4 take away 1, 2 take away 1, 1 take away 2, or 3, 1, and negative 1. So there you go. Thanks for watching all the way to the end. And just make sure that you've really got that distance from a point to the plane formula in your brain, because I'm pretty sure it's not on the formula sheet, but it's incredibly useful.